Hey everybody, this is Alex Merced, and welcome to another episode of Gnarly Data Waves. And this week's topic is going to be data as code with Dremio Arctic, ML experimentation and reproducibility on the Lakehouse. Now, before we get started, of course, some announcements. So head over to dremio.com and try out the Dremiotestdrive. Just click on that test drive button so that way you can get hands-on with the data lakehouse at no cost, no obligation in a few minutes, so that way you can see what the big fuss is about. But not only should you do that, but you should also be downloading an early release copy of Apache Iceberg, the definitive guide, an early release copy of this new O'Reilly book slated for release early next year. Get your early copy by scanning that code now. Okay, we got plenty of episodes coming over the next couple months, okay, such as Dremio and the Data Lakehouse table formats next week, getting started with Dremio data reflections the week after that, simplifying data mesh with Dremio's open data lakehouse, best practices for building a data lakehouse on ADLS, versioning data in the data lakehouse. Oh, so many great topics coming every Tuesday at the same bad place, same bad time. And of course, make sure to visit Dremio as we partner with AWS on the following events in Chicago, New York, and Toronto. So if you're here on these dates at these times, make sure to attend these events. You'll have a good time. But also, Dremio will be present at all these events across the world, whether it's Coalesce by DBT in San Diego in October, Big Data London in September, Big Data and AI Paris in September, Data Festival in June, and Big Data in AI World. Okay, so make sure to check them out. There's always cool swag at the booth, so definitely worth stopping by. And with no further ado, let's get on to our featured presentation, Data as Code with Dremio Arctic, ML experimentation and reproducibility on the Lakehouse. And to present, it's fellow developer advocate here at Dremio, Dipankar Mazumdar. The stage is yours.
Hey everyone, welcome to this new episode of Gnarly Data Waves. Our today's session is about data as code with Dremio Arctic, and specifically we'll talk about how machine learning experimentation and reproducibility can be achieved in an environment like a data lakehouse. So let's get started. A little bit about me. I'm currently a developer advocate here at Dremio, and right now I focus on a couple of open source projects like Apache Iceberg, projectnessie, Apache Arrow as well. As well as the Dremio's Lakehouse platform, that consists of the compute and the Arctic catalog, and that's why we are here today to talk about Arctic a bit more about. And my past was in like BI, machine learning, and data science, and currently I'm also co-authoring the first book on Apache Iceberg, so that's pretty exciting. This is on an early release program as part of O'Reilly's release, and that means you have access to this book right now as we write the chapters and make them available. So right now 2 chapters are already out, so I would highly encourage to go and look at it and basically gather some feedback. That way we can help make this book more robust and make sure those feedbacks are aligned. So in terms of the agenda, we will first discuss a bit about how experimentation and reproducibility are critical for machine learning. And then we will try to understand problems that we have today to really make these 2 aspects seamless and easy for data scientists and machine learning engineers. After that, we will see how a lakehouse architecture and table format like Iceberg and a catalog like Arctic basically solve some of this problem, if not all of them. And finally, we will introduce Dremio Arctic and see how it enables a data as code approach in a lakehouse architecture, and how that in turn helps data scientists and machine learning engineers to run experiments and build models with agility. We will switch between the presentation and live demo in today's webinar, so it's going to be like a mix of it, probably 80-20%. So yeah, you'll see me demoing Arctic. We'll go through the user interface of Arctic. We'll see how simple it is to run some query from Dremio's Lakehouse platform. And then also we will use a Jupyter Notebook environment that is for our experiments, where we will be basically building our machine learning models, and taking it from there. So let's get started. So unlike the software engineering field, which is usually backed by established theoretical concepts, right? We have established concepts in the world of software engineering. In the world of machine learning, it basically takes a slightly different approach when it comes to productionizing a particular data product. In that case, it might be a machine learning model that has been put into production, right? So machine learning is more of an empirical procedure to test a hypothesis. And what I mean by that is that let's say, take an example. Suppose we have a data set containing information about, let's say, houses, right? Including features like number of bedrooms, square footage, and location, and along with their corresponding sale prices, right? And we want to build a machine learning model that can predict the sale price of a house given these features, right? So in this case, the hypothesis could be that the sale price of a house is influenced by the number of bedrooms, square footage, and location, these features, right? So the machine learning algorithm will test this hypothesis by analyzing the provided data, that all the data that we provide as a training data. And it will learn the relationship between the input features, that is all these features like I talked about, the number of bedrooms, square footage, the location, and the target variable, which in this case would be the sale price. So that's how it basically starts with like an empirical procedure and try to test a hypothesis based on this particular relationship that it learns on the data. So it means that machine learning models rely heavily on a series of experiments to decide the success or failure of a project. And there are usually a lot of experiments carried out before a model can be realistically deployed for critical tasks in production, right? So, there are a lot of things like, for example, if you see in this particular screenshot here, this is a typical experimentation environment and a scenario where we have a lot of things happening here. And I'm going to talk a bit about it in depth later on. But the most important thing to remember here is that with experiments, right, there is also a huge probability to having to discard certain experiments to ultimately come to a point where the model finally makes non-generalized decisions. So that's the whole point of the building the model, because we are not expecting the model to remember something or memorize something and make a prediction based on that, right? That would be like a wrong prediction. So whether or not a model makes into production, data scientists still need to spend considerable amount of time in experimentation process, right? That's the kind of the main thing. And typically an experiment would involve, the process of changing values of one or more variables and observing the effect on the outcome. So for example, a classification model on a different training set can yield, different levels of accuracy, right? And depending on different data. So as you can see on the image here, obviously, we talked a bit, but like there are different types of models here. There is the code itself. There are different segments of training and test data, that is there. There are different features, hyperparameters. So it's a pretty messy environment, to be honest. So, but yeah, that's how, typically how an experiment would look like in the machine learning world as of today. So we have established that experimentation is the heart and soul of machine learning, right? And we also realize that the problem is like with any scientific experiment, machine learning experiments are super hard to keep a track of. That's like the main cumbersome point. Most importantly, we saw that there are a lot of components, like I said, they're super hard to keep a track of, like, the code, the hyperparameters, the models itself. You'll be building, to be honest, a lot of models to be really putting something out in production as well. So it's really hard to keep a track of these different components, as you can understand from even at a smaller scale. So here is a quote from a real world experience that I was reading, and I personally come from that background as well. So I also have that experience with building machine learning models and experimentation and stuff. So the situation can be we developed a highly accurate model after a series of experiments, but have a tough time figuring out what resulted in that particular accuracy, right? As we use different data sets with varying features in different environment. So some of the key things to take away from this particular quote is that they have developed a highly accurate model based on a series of experiments, right? And they have basically have a tough time figuring out what data set or what environment or what features that they use to build that particular model. So it's super hard. And also it's super important to understand that these parameters like to be able to track. Like these parameters that I kind of presented here, these are very hard to track at scale, as the number of experiment increases with you, right? In fact, most of the machine learning projects without proper tracking mechanism have a common problem, and that is figuring out what these variables are, what data set that you used, what features are used, what environment resulted in a particular accuracy of the model, or any kind of evaluation metric that you decide to evaluate your model on. And like I said, I personally, just to give an example, I have used in the Excel sheets to track my experiments, and that was super bad and super hard, just wasting a lot of time to figure out what data set I used, what hyperparameters I tweaked, what model I'm building. It's really hard to keep a track unless and until you have a system or a process in place. So providing data scientists and machine learning engineers the flexibility to run various experiments in changing environment is very critical. And that's what is the super important problem to solve for us. And, well, we have had MLOps, machine learning operations, for a while now. You might have probably heard about MLOps, but we have had it for a while. So we do understand that at least to some good level, these problems can be achieved by tracking two of the things. One is the data, which is super important. For example, the versions of the data, the commits, what changes in the data, what training and test set I'm using. So that is super important to track. But also the model, right? The model artifacts like the model pickle files, the configuration, the dependencies, and those kind of stuff. So the learning from the solution to this problem of experimentation is that you need to provide some, you need to be able to track two of these things, the data and the model. And you also need to be able to provide this flexibility to machine learning engineers and data scientists to be able to run these things in a smoother way. Now, moving on from experimentation to our second use case, which is reproducibility, right? And that's another critical aspect of machine learning, that you want to build reproducible model. So what is reproducible model? Basically, it's the ability to recreate and obtain consistent results from machine learning experiments. In a way, experiments are kind of related to reproducibility because maybe there is a model that you have developed based on a certain experiment, and it's a highly robust model, and you want to be able to reproduce that kind of model, in different data sets, in different environments, and those kind of things. So it involves, at a high level, it involves ensuring that the same code, the same data, and experimental setup can be used by different researchers or practitioners to achieve similar outcomes. That's the ultimate goal of reproducibility in machine learning. And reproducibility is very crucial, like I said, in most of the avenues. For example, in machine learning research, it allows for verification, validation, and to be honest, comparing the results, and in a way, it promotes transparency, right? And that's the whole point of our research, open research, right? That you want to be able to, for people to be able to reproduce the model. For example, you have built a really good state-of-the-art model, and you write a paper about it, and you publish the paper. And then an engineering team picks up a paper and tries to implement the model, but they end up not being able to reproducing or achieving the similar kind of result because of the problems that we are going to see now. So some of the problems that I kind of based on my experience and what industry is kind of talking about in general is that one is verification and validation, right? So like I said, why is it so important, right, in a machine learning world? Why reproducibility part is so important. So first thing that comes to my mind is obviously how do you verify the results of different experiments, right? Before we talk about this problem, it's important to get why it is also important in the industry, right? Not only just the research part of it. So one is that. And the second part is that reproducibility makes it easier to debug and kind of troubleshoot machine learning models. So let's say if an issue arises in the deployment or operation of a machine learning system, having those reproducible experiments enable developers to pinpoint the exact source of the problem and understand the factors that can basically contribute to the issue. So in a way, you're able to reproduce, debug that issue using reproducible models before we put that into a production environment. Also, reproducibility facilitates collaboration and knowledge sharing among team members and across different teams within an organization. That's something that's again very important. And another important thing that comes to my mind on top of my head is that when you're trying to scale machine learning based system in production, and you're trying to maintain the performance over time, it's important to be able to have those reproducible models because you want to be able to achieve those similar results even when you scale the system and even bringing in different users or different features and stuff. So that's super important. Again, but there are some problems with reproducibility today, and we are here to discuss about it and see how we can solve it using Dremio Arctic and some kind of tools here. So one of the problem is that there's a lack of complete documentation. So insufficient or incomplete documentation of the experimental setup. It's ideally expected that you would be documenting those things, including the code, hyperparameters, dataset pre-processing steps, if any, software dependencies, and those kind of stuff. Ultimately, the goal of this particular documentation would be to be able to reproduce the results accurately, right? And second, like I said, with versioning and dependency management, right? In a machine learning model, often rely on various libraries and frameworks and external dependencies. So if there are inconsistent versions or unmanaged dependencies, that can lead to discrepancies in results between different environments. So again, a very important factor to consider when you're trying to reproduce model. The most important thing among all these things is the data itself, right? Reproducing machine learning model experiments require access to the similar or kind of same data sets used in the original kind of building the model. However, data changes with time. Either some new ETL job has brought in some new records, either you have added some new features over a period of time, but you still want to be able to achieve the similar kind of like, evaluation metrics like accuracy, when even if you like change the data and like, even if you have a different kind of environment and setup. So data is one of the most important aspect that you should be super critical about, like, because that's what helps you like ultimately build models, right? That's the whole core. And then the environment in general is also very important, because with different varying environment, you will have varying like hardware configuration. Probably it can lead to different results. So the type of configuration you use also is super important. So and we are going to see and like we are going to see in action how these kind of like things are taken care in our current solution, and how we can take care of these problem with the newer approach. Again, here is a quote that I have personally seen it, and based on my experience. So it's like we are trying to achieve similar precision and accuracy using the same model and code that was released by our ML research team, or basically our ML team, but on a similar data set, right? But we can't seem to replicate. So that's again a common thing, right? It's tough to verify those empirical results and claims made by a specific research paper, or some model that has been already put into production by your team, and to be able to reproduce the experiments carried out in them. So it's super hard for that. Also, for machine learning models to be put into production in an entire enterprise environment, it is crucial to be able to replicate those results, right? Based on those evaluation metrics like accuracy or precision, and whatever those metrics are, depending on your goals. It's important to be able to reproduce those results based on that, so that you can ultimately put that model to production. So again, these problems could be solved by being able to track a few of this component. Like I said, the code itself is super important to be able to track that the data set, entire data set, different segments of the test set, the train sets. It's super important. And the experimentation environment, we learned about that a bit. So these three things are super important to be able to like track these things, and so that we can easily reproduce machine learning models. So in this particular talk, we will keep our focus on the data artifacts, and because data is basically the core to training and building a robust machine learning model, it is non-trivial to kind of focus on this particular component, specifically for when we're thinking about like architectures like data lakes and data lakehouses, which are mostly used by data scientists and machine learning engineers. But again, like, the other two components like the code, for example, can obviously be tracked using GitHub, something like GitHub, or, there are also like notebook integrations as well now. So you can basically integrate Jupyter Notebook with a tool, and, they can keep a track of the code as well as you push it. And then for model artifacts like, like hyperparameters, like the model file and dependencies, those are the artifacts you can track using tools like open source tool like DVC and stuff. Again, there are also paid solutions around that. But our focus would be like, how do we track the data part of it, and how do we use the data part of it to like build robust machine learning models through experimentation, and be able to reproduce this model. And that's why we're going to use Arctic for that. That's the whole point of this talk. So coming to our main point, how do we basically support experimentation and reproducibility in a lakehouse architecture? We are talking about data lake and lakehouses. So we know data lakes are basically one of the main source of information for data scientists and MLEs to like access data and build models, right? And sometimes there is a feature store on top of that, which is basically transfer of data. That's what a feature store is. But in general, for data scientists to be able to like build models, they will need direct access to a data lake storage, similar like a data lakehouse, and they can use that data to build the models. So just to give you a refresher, and I'm assuming most of you are aware of the data lakes and data lakehouses environment and architecture to some extent, but I'll just give a high-level picture so that it kind of remains as a mental picture as well as I end this talk. So I'll start from the bottom like to the top. I usually like take it from the bottom to the top to just explain what the different components are, and so just let's quickly take a look on that part as well. So on the extreme bottom part, you have the data lake storage, which is basically your can be a S3 bucket, it can be Google storage or ADLS, or even like on-premise system like HDFS, a file system, right? And on top of that, you have the actual files, which is basically the files that are holding your data, right? And these can be different file formats like Parquet or ORC or CSV, JSON, any kind of like file. So, it can be structured data, non-structured data, whatever it is. But in this case, obviously, like we are going to talk primarily about tabular data. And on top of the file formats, you have basically the table format. This is where a table format like Iceberg comes. And that's what ultimately enables like the whole Lakehouse architecture. So in a nutshell, Iceberg takes care of like the metadata management. So like tracking different data sets, which would be hard to track in a data lake environment. And that's why we kind of like move from a data lake environment to like data lakehouse, because, it's really hard with like, doing governance and stuff in a data lake, because usually it's more of like a storage and a dumping space. So there are really no governance or data quality. And unless and until you have like a quality data, you cannot really use it to like build a model, because ultimately the decisions would not be reliable and stuff. So again, we are going to learn a bit about these use cases and how Iceberg basically enables those use cases. But another thing is that when data scientists, they directly access data from like raw data from the data lakes, it can be very slow, depending on the compute engine and programming languages, like whether it's Python or something. So it can be really hard to like access the data, specifically because MLEs and data scientists need normally a larger amount of data, unlike the BI world. So accessing that data using ODBC or JDBC might not be the right protocol, and you might have to use something like Aeroflight. So that's very cumbersome as well. Whereas with Iceberg, you have various pruning mechanisms to like limit data reads and stuff, and ultimately avoid scanning more amount of data using those metadata files, thereby making those read faster. So that's about Iceberg in a nutshell. It's a table format. It's basically managing all those file formats that are below that level. And on top of the Iceberg table format, we have a component called catalog, which is a modern metastore, which is something that we require for Iceberg table that brings also in a Lakehouse environment that helps you to keep a track of all the tables and the metadata that is there in your environment, right? So one of the important things with Iceberg is that with normal file formats, you don't have those atomicity and consistency guarantees, right? When you're, for example, multiple concurrent writers are writing data to the same kind of like file, it's hard to like, log that thing and, be able to maintain those guarantees. You don't know whether those writes will be successful, whether there might be some bug or, some partial writes and stuff. So, it's really hard to do those guarantees, specifically those ACID properties. Whereas Iceberg brings those properties, and it does that using this particular catalog part. So this catalog, and this Iceberg ultimately enables us to like, do those things like, for example, like branching and, those capabilities that we are going to talk about it today. So catalog can be a lot of things, like, it can be, in a simple term, it can be a database or a data store that basically has some kind of a locking mechanism, like I was telling, like, you just need that mechanism to like be able to maintain those guarantees in terms of like writing and concurrent writes and stuff. However, not every catalog brings those capabilities like data versioning and doing things like branching, which is our focus today. So Dremio Arctic is one such production-ready catalog with these capabilities. And it allows us to do things like experimentation and reproducibility in machine learning in a Lakehouse environment. And we're going to see more in the next slide about how it enables that thing. So ultimately, these two things enables a data as code approach. The whole point is that you kind of manage data using a code-based approach. And we are going to see how do we do that. So if we go back to the software engineering world just for a moment, it's hard to imagine developing code without a version control system like GitHub, like, just to give a comparison. And, it's really hard. Like if we take a world in which we put our source code in, files in a file share, and that's how we push software, it would be really tough, right? It's super hard. And to be honest, that's how kind of we are working with the data environments today. And, so there is a need for this kind of a system that kind of helps you to achieve some kind of a control in the versioning and maintaining those versions, right? So what enables software engineering teams to achieve all of these, basically these things that we're going to discuss about in a moment is that, there are things like consistency, right? You have with GitHub, you have a consistency of the whole environment. That is the whole code space. And really be able to do things like in isolation, like we discussed with the local branching, right? So you basically in a GitHub, what you do is like you have a main branch and you create a local branch so that you can do your own features building. You can, add in new features, or for example, like, improvise something, right? Some code. And if those features are, building is done, you basically merge that particular branch to the main, deciding on the code review and everything. It will, someone will help you push that part to the main and, bring those data to production. So we want similar things to be done in the data engineering world, right? We want to be able to be able to do our local branching and have a bunch of engineers work on a single branch and do some ETL or do some experimentation. And based on if we decide, okay, this is good enough for us to push it to the main, let's push it to the main. Let's merge it. That's the whole point. And then, obviously with experimentation, that's another important aspect. Like that's our focus today. Like we want to be able to experiment without any barrier, without any, impacting any kind of production workload. So that's super important. And most importantly, the ability to verify those changes, right, before you push them out to production. Like I was telling you, right, in software engineering environment, you have a process in place today, right? You have QA involved, you have various tools involved that make sure those checks are kind of passed and finally helps you get that to production. So Dremio Arctic basically tries to do the same thing through very similar functionality, actually. So one of the things is that it brings commits. So these are kind of atomic transactions that affect multiple tables or views at once, and we're going to see more about it. So what commit basically is at a high level, it is a state of the whole environment. So you can say that, hey, I have a commit at this point of the day and time, and I can take a look at the entire environment at that point of time as of that particular commit, right? You can basically take a look at that particular data environment at that table at a more granular level, and we can basically refer to that particular commit at any point of time because that's a commit. And also you can create branches like I was talking about, right? So this is branches on the data lakes. And I'll talk about this more specifically, but basically you can create a branch of your entire data lake environment, and it's a free and virtual copy of your data lake. So ultimately, you're not making any extra copies, but you're basically just referring to those different versions of the branches or different versions of the table. And then you can do your stuff like for example, experimentation and stuff. So you're free to do that. It also enables the use of tags, same way as there are GitHub Git tags, right? Where you basically, for example, in Git, what you do is basically you label a specific version of a commit and say, hey, this is a tag, So it's an immutable reference. That is, you cannot change a tag. So let's say I kind of do some ETL and, insert some new records to a table, and I label that particular commit as a particular, tag. So I can refer to that tag later in time and use it for my experiments or, use it for some analysis, or using it for some kind of in production with my dashboards or with models. So that is super important to have, and it borrows a similar concept from the world of Git with Arctic, as well as it merges, right? Again, similar to Git merge, right? You, for example, do your experiment, and since you don't want to expose the new data or experiment to production environment yet, you can just work on your isolated branch and then decide to merge this branch to the main when you decide to, right? When you're sure, okay, now I have done my experimentation. I think this is good enough for me to push it into main and for making it available to others. So let's then merge it. So that kind of a flexibility right now is absent, and that's what Dremio Arctic kind of targets and bring those capabilities to the world of data. So before we explore more on the Dremio Arctic, it is important to note that Arctic is actually built off an open source project called projectnessie. So basically, Nessie is a project that we built in-house in Dremio a couple of years back, and then we outsourced it, made it open source. And so Nessie brings in a Git-like experience for data lakes or lakehouses. So all these features that we were talking about, with the commits, tags, ultimately, with Arctic, it's built on top of Nessie. So it's service, and it obviously has a lot of other features, but that's what is kind of good, and just to have an idea of what it's built on top of. So you can explore more and see if that helps. So Dremio Arctic, like I said, Dremio Arctic brings these capabilities with data versioning and such, and enables a modern approach to data management, and ultimately brings in a Git-like experience to the world of data. So a couple of things that we want to focus on today is isolation, version control, and governance. So one of the things is isolation. That's our prime focus. We want to be able to create our isolated branches and be able to experiment with our data and build some models and run some experiments without impacting other users or any kind of production workload. So that's important. And second use case obviously can be you are ingesting or transforming the data before exposing it to other users. So you do that in isolation. And as you can see in the screenshot, once you're done with creating your branch and doing an experiment, you can merge it to the main environment. And I'm going to walk you through how to do that in the Dremio Arctic UI as well, and from a Jupyter environment as well with Spark. And obviously, like there is the version control. That's again a very important part of it. Until this point, we didn't have any kind of a data version control. So it's important that we keep a version of this data. And this is where things like commits come into picture, and we are tracking those commits and be able to refer to those commits so you can reproduce models or dashboards and based on those historical time or tags. And also you can recover from any mistake, right? For example, like there is some kind of like mistake on your environment. An ingestion job, for example, leads to like some kind of a bad or zombie data. You can easily recover from the mistake, by basically instantly undoing those changes and reverting back to previous commits. So that's again a great flexibility, and all the historical information is maintained in like the Arctic's version control system. And the most important part, which is like the governance part, right? And all this time with data lakes, we didn't have any governance at all, and that was kind of like the main problem, right? So we don't know who changed the data, what changed the data, what impacted it. So it's really hard. Whereas in Arctic, with Arctic, all those changes with the metadata and the data itself are tracked, and basically you can see who has access to the data, who doesn't have, and also you can give the privileges, like you can give the access controls based on a particular data on the table or a column or row level kind of thing. So there are different kind of access controls, and you can decide to give access to people depending on their roles and everything. So it's that is also like super helpful for an environment like Data Lakehouse. So now we will kind of switch gears and do some kind of a live tour of Arctic. And like I said, we will run some experiments. So I will switch from Arctic to a Jupyter Notebook environment with Spark as the engine, hopefully, just to show the seamless integration kind of with different technologies and stuff, and how it flexibly enables data scientists and MLEs to like basically do experiments and run reproducibility with the data part of it. So the focus is on the data part. So before we start, just to give an idea of the setup, and like just coming from the previous picture that I had with like lake houses, it's important to know what we are building and what we are using in terms of the technology. So this is what our architecture looks like, and so I have some of the data today in my S3 bucket, which is a data lake, and specifically I have two CSV files. Again, this can be any file formats. There is no limitation to that, but I have two CSV files that I'm going to use it for this particular demo. And then on top of the file formats, I have the iceberg table format. So I'll be creating iceberg tables so that I can easily manage those file formats and be able to take advantage of things like schema versioning, metadata management, schema evolution, and those kind of things easily. And for the purpose of like how to show like how flexible and how multiple engine can use the data from different for the same data set, we will use two engines here. One of the engine is Dremiosonar, which is what we are going to use to create iceberg table and read some of the data. So a Dremio Lakehouse platform has two components. The Dremiosonar is the compute engine, and Dremio Arctic is the catalog. So we are going to use the Dremiosonar to create the tables, and we're going to use expose those tables using Arctic catalog. And we're going to use another engine called Spark, like apacheiceberg, which is like pretty famous. And then we're using Spark to basically get into a Jupyter Notebook environment, and then use scikit-learn to build our machine learning model and see how we can use the flexibility of Arctic for experimentation. And like I said, on the right-hand side, there is the Arctic catalog. This is how we are exposing the different tables, all the iceberg table that I'm creating in my environments, so that multiple tools like in Spark and Dremio or any other tools can easily access the table. So the most important thing to note here is that our data is in open formats. Like, our data is in open table format like iceberg. So multiple engines can use it for different tasks. I can also bring in, for example, a streaming engine like a Flink, Apache Flink, right? And just sit on top of this particular engine list, and it will have direct access to the iceberg table. So this is the flexibility that we have with open table formats and with the Lakehouse architecture like this, with iceberg as that kind of table formats, and catalogs like Arctic. So that's the overall setup of the environment. Okay, so just so I go, before I move to the actual demo part, you can basically, just to get started with the Dremio Arctic and Sonar in general, you have to sign up for DremioCloud. It's pretty easy, it's like list of steps, and you can just, follow this instruction. I can also share an article, which is really easy and provides a user experience to go and learn about how you can easily set up. And once you're done with that, you can basically go to the next step, which is connecting to the data lake. So like I said, our data is in an X3 bucket. Those CSV files, as you can see, they are highlighted over here. these two CSV files are there in my data lake called Dipankar, and then those are a S3 bucket that I already connected to my Dremio environment. And my ultimate goal would be like to connect to that data lake and be able to read those tables and create iceberg tables from that. So for now, let's pause on this particular slide and let's go back to an environment where we can see what things look like on our Dremio environment. So this is where I'm in Dremiocloud, and right now I have different projects here. Obviously, like these are my catalogs, the different catalog that I was talking about with Arctic, and these are my different spaces or like kind of semantic layers here, so that you can make sure data is in a particular format. And here are my different object stores. Like I said, you have to basically add a source here. If you're trying to use a S3 bucket, you can basically connect to this particular source, and you can provide some details over here, and you should be able to connect it. For now, I already have a bucket that is connected over here, and I'll go to my datasets folder, and I can see my 2 datasets that I'm going to use it for my experiments today. And obviously, as soon as I get it here, Dremio makes it super easy. For example, I can, see the lineage, right? That's super helpful as well. So for example, I can see, okay, my data was in S3 bucket, and now I have, created, this data set that is connected from this S3 bucket, and these are the fields that are there in that particular table right now with this data set. So these are the 2 data sets that we have right now, and my first step, like I said, would be to create 2 iceberg tables based on this particular 2 data files. So one of the easy way to do that is you can basically click on this particular 2 data sets, and once you do that, it will open up these things. And there are obviously like 2 options to do that. Since these are CSV files, you can use the latest copy into command, and basically it will create a table. But yeah, one of the common things to do is like just say, hey, create a table. I'll say Arctic, the catalog name, and I have a folder called ML demo, and I'll give the table name as, for example, let's say churn, and I'll say as select star from this particular data set. And as soon as you do that, what Dremiosonar will do is convert this CSV file into an iceberg table. And I'm not going to run this because I already have 2 tables already. But the statement basically is the same that I use. And once I run this particular statement, I should have this table in my environment. So now if I go to my Arctic here, and inside the Arctic catalog, I have my ML demo folder. Obviously, you can have folder or you cannot, but it's your choice. But once I go to this folder, I can see 2 iceberg tables here and that I used to create based on the 2 datasets that I had in my data lake, those CSV file. So one is the churn and one is the churn October data. And as you can see, they have an iceberg icon. That means they are iceberg table. So if I open this up and, for example, run this particular select star from Arctic, this particular table, the Dremiosonar will execute this particular query and it will return the results. As you can see, there are 20 columns, and Dremio returns the results. I can see the number of rows here. So yeah, super important and super convenient to like be able to create. Basically, you saw how easy it was to create an iceberg table and like execute that and take it from here. So Dremio makes it super easy as an interface to do that. So now, obviously in a real world environment, maybe data engineers would be typically they would be responsible for creating iceberg tables and making a data set available to data scientists. I personally, for this particular experiment or for this particular demo, I'm considering like myself on the shoes of a data scientist. So I'm imagining like, those tables have been provided to me by the data engineers. So yeah, so that's pretty much it. Like, so we have our tables now that are already created in my Arctic catalog, with this particular 2 tables CSV files. So now my data for now, like, we have connected this particular table, and as you can see, these 2 tables are already created here. So my next step is basically for my experiment, because I'll be, building those machine learning models using a Jupyter Notebook environment and in a different experimentation environment. What I'm trying to do is like, I have created a Docker image, and I am basically going to host a Jupyter Notebook within that Docker image. So typically in the real world of like experimentation, that's how it typically works. Like you have some kind of a container, and inside that container, you either have your code in some way, and you basically share that container with other people so that they can use the same kind of environment to like, build the experiments and reproduce the results. So I have tried to basically replicate the same thing. So, this is what we are going to see more about this. But in general, what I'm trying to achieve with this configuration in my notebook, and I'm going to go to the notebook in some time, but I'm going to try to connect Spark, Arctic, the catalog, and Iceberg. And this is what I'm trying to achieve with this setup. Again, pretty much boilerplate. you don't have to worry about like this configuration. It's all boilerplate, that it's all a template. So I actually have a blog around that is pretty much detailed. I think it would make sense for me to, share after the presentation so that you get an idea. And actually it also has the Docker image. You can basically like pull the Docker image and start with your iceberg environment and, connect to a different catalog, like for example, Arctic, and then you can easily get started, or use something open source like Nessie as well. So just to go over a couple of parameters, obviously we have a configuration with Iceberg and like the Spark runtime, and then with the Nessie for Arctic, and then we are going to create a catalog called Arctic here, as you can see. And then I'm telling it's a Nessie catalog, and that's what I'm telling Spark to do. And I'm also creating a warehouse directory and providing the location here because I'm going to write some data, right? I'm going to probably like make some changes to the table and add some new changes and those kind of stuff. So that's where all the writes are going to happen in this particular S3 bucket. And the next set of configuration is the Arctic server. So basically, if you go to, for example, here to my Arctic catalogs, this is my catalog. If you go to the settings, again, these information are present in a blog, and I can share all this information. So you will get the catalog endpoint over here, and you have to basically copy this catalog environment to your Jupyter notebook, and you can just add it here. And to connect Arctic, which is in a Dremio's environment, we are using an authentication mechanism. We have proper authentication mechanism in place so that right people can access the right set of data. So I'm using a bearer token mechanism, and I'll pass the token over here. You can easily get that token from Dremio's environment. So for example, if you go to here under Sonar, and then here, you can go to the account settings, and you can generate your personal access token from here. So once you get the token information and supply it over here, you should be able to enable the extensions, and you should be able to be up and running with the Jupyter Notebook environment. So once you have this configuration ready, and I already have this configuration ready in my Jupyter Notebook, as you can see, I have certain parameters here, but I have all these settings over here. And now I have Spark running, which means my environment is all connected. So by this point of time, I'm already connected to Spark, Arctic, and Iceberg. So my notebook is connected to these three things. So now if I try to, like, for example, like execute a command, I'm going to talk about a bit about this particular command, but let's see like if our environment is working fine. Okay, it was able to work fine. So as part of the first step of this particular experimentation use case, let's go through. So we'll go through two of the use cases. So for our first use case, which is machine learning experimentation, our goal would be to like train a classification model, a churn classification model with reduced features. Basically, our experimentation goal would be like to take a data set and either to like add some new features or remove some features. For this exercise, we are going to look at removing the features and then compare its accuracy with our baseline model. Hypothetically, let's say it's 92%. So if we gain improvements based on this particular new improvised data set, then we will make the data set available to the main branch for users by other data scientists and other teams within the organization. But alternately, if we don't see any improvement, we are going to like discard the experiment, right? So that's our entire goal. But obviously, without pre the Arctic environment or like pre earlier days with data lakes, this isn't really possible, right? You would be typically like do something like you would either access the data directly on S3 bucket, and you'll just either make a copy because you might probably not have access to like write data to that particular alter the data set, right? So you make a copy of the data set and you have to maintain that copy, and based on that particular copy you have to build a model and see how you can basically find out a way, figure out a way to like make that data set available to other users as well. However, with Arctic and Iceberg, what we are going to basically do is we are going to create an isolated branch, right? An isolated environment where we can run our experimentations, right? So we do something like a create branch, and we have our own environment with a zero copy version of the data set. And once we have that, we can do whatever we want to that data set, and we can experiment it in a way that we like, build a model. And if we decide that the data set is good enough and our accuracy is improved, we are going to make that data set available to production by merging that particular branch that we kind of created, right? And if we decide that the experiment was not successful, it wasn't good, we'll just drop the branch, and that's it. We're done with it. We have no liability in general. So let's see this in action and try to understand what happens in our Jupyter Notebook environment here. So let's say I'm in the main branch right now. You don't have to by default, you are in the main branch. This is the connection that I have. Obviously, I can see all the list of the branches over here. If I execute this particular command, which is list of references in Arctic, it'll basically give me all the branches that I have right now in my environment. So I'm going to say create a branch ML experiment for this particular experimentation use case. And once I do that, Arctic will create a new branch and it will assign a hash. And this is how Arctic is basically internally tracking it. And I have a new branch here, ML experiment. So if I go to my Dremio environment and go to my Arctic catalog, I can basically see a new branch over here, which is called ML experiment. And remember, my two dataset actually were in the ML demo folder in the main. These are the churn and the churn October data. That's the two dataset we're going to use today. So instead of like using the data from a production environment, I'm now created my isolated branch. So I can just go over there and I will have the same data set, which is a no copy version, like I said. And if I open this particular data set, I can basically see that what my data sets records are. So I have 20 columns right now. There are a couple of records over here, and let's try to do that in the Jupyter Notebook environment. So once I create a branch, I have to, since I'm right now by default, I'm in the main branch, I have to basically change the branch, switch it to my new branch. To do that, I'll just say use reference this new branch. And once I execute this, I'll be in my new branch. Okay. And now if I do like a select star from this, I should be able to see the same record as we saw here in Dremio interface. So obviously, now we are using like Spark and as a query engine. So, we are going to see what happens when we are kind of using Spark to like load the data set, because ultimately, the whole point of this exercise is that we're going to use multiple engines to like train, use different kind of applications and models. So once this particular this particular data loads, then I'm going to like just alter. I'm not going to like do a demo of the entire thing, but just to give an idea, like I'm going to basically drop a couple of the columns as part of my experiment. Remember, we talked about how you're going to use a reduced version of the data set, because let's say based on our initial analysis and our kind of like exploratory data analysis, we figured out that some of the features are highly correlated, so we don't need all the features. So we might want to just drop a couple of them, right? So the most important thing to note over here is after I execute this alter table and drop this particular column from my table, I am actually not impacting anything on the production table, right? As we can see, we are basically in our own local branch called ML experiment. So now that the table has been deleted, now if I go to and execute this particular command here and do a select star in Dremio, I should be able to see only 9 columns because I have basically dropped out all the unrelevant columns for my model to be trained on. So if you give a couple of minutes here, you can see here only 9 columns we have, and we have this many records now, so that's really good. So now if I go and use Spark to basically read that particular table, we can just basically put it into a data frame for putting it into our machine learning model. So we're going to just do that. And as you can see, Spark is basically reading it to a particular data frame right now. And after that, we're going to like just see idea, this is the data set that we have right now. And I'm going to do a dummy encoding. Again, I'm not going to go deep on the model building part here because I'm assuming you have an idea on that part. So I'm going to just show what happens just when I train the model. So the model is being trained right now. It's a random forest classifier. So yeah, again, the choice of model can be something else as well. So we have right at this until this point, we have basically used a reduced version of the data set that we kind of use for our experiment and trained a machine learning model, right? And if we do an evaluation, we can see that the model accuracy is 82%, which as per our initial goal was 92% baseline, and it didn't meet our goal, right? So that means our experiment wasn't really successful. So our data set is not good enough to be made available to production. Even if you do something like hyperparameter tuning, the best parameters that you get and the best score that you get is 87%. That's not good enough. And once I'm done with the experiment, because I'm not going to use this particular branch to merge it, I will just drop that particular branch from my environment using this command drop branch. And if you go to now our environment in Dremio UI, just to see how it looks like, you can see that the branch is no longer available because obviously we have deleted that branch. So I'm going to just use the main branch. And just to make sure our table that's in the main branch, that's totally intact. There is no harm in this particular table because of whatever we did. So it's all in line. Obviously, if you wanted to, if our experiment would have been successful, we would have productionized it and we would have merged this branch to main. And all we had to do is merge branch this particular name to the main, and that's all. That's all we had to do. Now, for our second use case, which is ML reproducibility, and the whole point of this particular reproducibility exercise is to basically take a model and use it on 2 different versions of the data set. Okay. And we're going to go through the same process. We're going to create an isolated environment so that we don't impact our main table, production table. And based on that particular branch, we are going to create 2 different commits of the table. Hypothetically, for this particular demo, we'll assume that one version is after we kind of ingest some more data after a ETL job. So let's try to do that. So I'll go to the Jupyter environment once again, and I'll just say, now I'm in the previous branch. So I'll just go to the main branch and just switch to the main. I'm going to create a new branch called ML Repro demo. And then that should create a new branch over here as well. As you can see in here, we'll be saying ML Repro demo. So that branch is here. So we are all good with our copy and everything. And now we can basically, since we have, like I said, basically once I create this new branch and go to this particular branch, I already have my tables over here. Right? Now in this particular use case, I'm going to use the churn October data. And this is, imagine this is the data till the month of October. Okay. So we have like 20 columns, 935 records. Similar thing over here. I'm going to just label this particular commit up version so that any new commits that happen after this doesn't impact this version of the table. So I'm going to just say, hey, create, October month tag. And I'm going to just label it, create October month tag. And once I do that, and I use that particular reference tag to understand the number of records, I should be able to see the count of 935 records. So basically, I use the tag to reference because, I want to make sure that I'm in that particular tag version of the data set in that particular commit. So that's what I did. And after a couple of minutes, I see the record as 935. So now let's hypothetically, let's say that we have a ETL job ingesting some new data to that table. So we bring in some new data and new features and stuff. So I'm going to go back to that repository that was called ML Repro demo. And I'm going to, just to mimic that scenario, I have a CSV file that has some new records. So I'm going to just insert the 2 records, okay? And I'm going to insert it to that October data table, which is this particular table. So now the insertion job is running, the ingestion job is running. Give it a couple more minutes, and then I should have the data in that new table. So Spark is still executing. And once I finish this particular step, it will insert. So here we created a temporary view. That's a really good practice to insert some data without really, making any impact of anything else. And once I do this, Spark will basically insert the records. And I should be able to even query that record from Dremio over here after I do that. So, the flexibility with like a Lakehouse environment is that, since you're using like an open table format like Iceberg, basically it's accessible to those 2 different engines. Like, we are basically switching from Dremiosonar to Spark. So that's really great. So I'm going to just label this new tag as a November month data so that we know that this new insertion job brought in this new data. Okay. And now if I use this particular tag over here as a reference and get the count of the number of record, I see the count of the record. Okay. And if we run this count, now we should be able to see the newly inserted record from my ingestion job. So it brought in 300 records. So now we have 1235 records. Similar from here. Even in Dremio environment, you should be able to see 1235 record now. So now it's the same thing. So now at this point of time, we have 2 data sets. One is the October month data, one is the November month data. So I'm going to use these 2 different data sets to build our machine learning model, to use our machine learning model and see if we can reproduce the the model on these 2 data sets. So I'm going to say use reference this. And then I'm going to load it to a Spark table like we did in the previous exercise with experimentation. We're going to put it in the data frame. And after we put it into a data frame, we have, like, just to confirm, we have 935 record. I'm going to drop a few of this column, do some dummy encoding, prepare the table, and then train our model. And once we train our model, we should be able to see the accuracy of the model and how it behaves. So right now, our baseline model that we brought, this particular same random forest model, has the accuracy on 92% on other data set that we kind of trained that model on. And we want to see where the same accuracy can be achieved on this particular 2 different version of the data sets. So as you can see, the model has completed training. And if we try to figure out the accuracy, it's 94%, which is good. Like, our baseline was 92, but the model was able to get some more, accuracy over here. And similarly for the November month data, I'll do the same, use reference this. And I'm going to go through the same process. I'm not going to run it again, but in general, the accuracy that I've observed is 96% with the new November month data. Again, the accuracy has improved from a baseline model. So that's really good. So ultimately, what we were able to achieve through this particular exercise is that we were able to bring our model, which we had a baseline accuracy of 92%, which is good enough, to bring it to different data sets. And how Arctic enabled us to do that is by creating different tag version of the data set and allow us to be flexible in using different models for reproducibility purposes. So that is pretty much that I wanted to show in terms of the value gain. I guess with the experimentation part, we were able to flexibly experiment. We didn't have to worry about impacting any production workload. We knew the data set was not good enough for us to promote to the branch, so we dropped the particular branch. Similarly, with reproducibility, we were able to create tag version of the data set, and we will keep a track of this tag version, and it really went up well. So that is all. If you have any questions around this, I'd be happy to take. And thank you so much for today.
And we're going to begin the Q&A session. Okay, so first off, we see a message thanking you, Dipankar, for what was an amazing presentation. So thank you very much. So
sure.
Let's mark that one as answered. Okay, and there's another thank you, so that's cool. Okay, so let me mark those as answered. Okay, we have a question from Jordan Milushev. While merging, how are potential data differences in the two branches handled?
Yeah, so I think internally, like, and Alex, you can add to that, but ultimately, I think it depends on basically those manifest lists and the manifest files, and whether like how they are tracking it, whether they are like, data records are to be appended or removed. So I think it all depends on that. But do you have anything to add to that? And also it follows the kind of conflict resolution policies, if there is any kind of like, conflict to the branches and how you can resolve it. So that is taken care by Iceberg spec as well.
Yep. Okay. So basically, yeah. So that's 100% right. Where basically right now it's doing sort of like a shallow commit or shallow merge. So generally, like best practice with the state of Nessie currently would be to have sort of for ingestion, have a single ETL branch. Then you're going to kind of avoid any merge conflicts whatsoever. Right now, if you start trying to do ingestion across multiple branches, you probably are likely going to hit merge conflicts and hit walls. What part of the project's roadmap is to start capturing more catalog level statistics. So that way, using those catalog level statistics, you can create more complex sort of merging logic. So that way you run into merge conflicts. You won't run into merge conflicts in more complex patterns. So, but right now, I would just, say create an ingestion branch, do your ingestion on the branch, then ingest it. And then generally any experimental branches are just experimental branches. There's no intention to merge. So you shouldn't run into any kind of merge conflicts and tags and things like that.
Right. Also, just to clarify on that, like obviously as part of this particular demo, like the whole point was to show just to like add some record and show the differences. But like you said, for like things like ETL and stuff, it might be a good idea to like, do kind of like shallow thing.
Cool. Now, how could I use Nessie to do? I mean, how could I use like Dremio Arctic to do data quality checks, like a write audit publish pattern? Is that something I can do with Arctic?
Yeah, for sure. I mean, like in a way, actually, because you are doing things at a catalog level, it's actually better because it has more controls towards it. And apacheiceberg by default provides ability to do that. But now, since you're able to do that at a catalog level, I think you can, there is an ability to like do that data quality perspective from multiple table perspective as well. So you can basically, bring in a third-party data quality tool. You can write data to a particular isolated branch and run your quality checks for multiple tables at the same time. And that's a great way, like to just be able to check quality for a couple of your Iceberg tables.
Okay, awesome. Let's see. Okay, and then I guess last question is sort of like, how would this be different than me like tagging a table with the new sort of native branching and tagging capability in Iceberg tables?
Yeah, that's the difference between the native capabilities of branching and tagging is that like that applies at a table level, while Arctic works or the Nessie works at a catalog level. So I think the whole point is that you have the entire code space for the entire environment of the data lake, because now you're using a catalog on top of that, and you're not just dealing with one particular table. So I think that's the difference, and I think it's also like from like my experience of like working on both the part, I think it's also more agile, like to be able to like create a complete code space of your environment and be able to do things like in isolation. But again, if your use cases are just limited to, for example, being able to just commit a label a particular snapshot in Iceberg and use it for like GDPR like audits, right? That might be something where you want to use like the native capabilities.
Got it. Okay, really cool. Okay, yeah. I think we're pretty much just short on time. And now, for those of you who are excited about Iceberg and all this fun, cool stuff, next week we'll be talking more about table formats. We're going to be talking about sort of Dremio and its story with different table formats. So we're going to go over, what is Iceberg, what is Apache Hoodie, what is Delta Lake, sort of like what is Dremio's functionalities with them. If you're using one of these formats, how would you use Dremio? So be there next week, same bad time, same bad place. Again, this will be posted on Dremio's YouTube channel at youtube.com/Dremio within 48 hours, and will also be available on Spotify if you subscribe to the Gnarly Data Waves podcast. But again, always love to see everybody. Again, thank you again to Pankar for a great presentation. I'll see you all next week.
Thank you, everyone. Right. Take care. Bye.